Hello everyone, my name is Joe Sack and I'm a program manager for the SQL Server product team. And today we're going to be talking about SQL Server vNext and adaptive query processing. So to help frame the discussion, we're going to talk about plan quality and cardinality estimation. And the first thing to understand is that query performance is dependent on overall query plan quality. So my plan quality is basically the join ordering or operation ordering, and then also the actual physical algorithms that I select for a plan. And those are extremely important for overall performance. And it's heavily dependent on cardinality estimation, or CE for short. And the idea here is that I want to know the number of rows that might be flowing through the actual query. And if I estimate it properly, then I can do things like properly select a join, properly order the actual operations, and so on. So the CE is actually in a very involved process, and we have some statistical calculations that we perform to get cardinality estimation, and we also go through a few assumptions, and sometimes we get it wrong, and so hence we have this new set of features around adaptive query processing that I'll talk about today. So in terms of risks of misestimation, so let's say I get the estimate wrong. I'm estimating 100 rows and I get 500,000 rows. What are some of the consequences of that misestimation? So first of all, you're going to get a plan that might not be appropriate for the actual task at hand. And then you might see situations where your query doesn't perform as well as it should, or you're using excessive resources. So I'm using excessive CPU, memory, I/O, and so on. And then also in terms of overall performance, if you look here, you have reduced throughput and concurrency. You might think, well, this only affects my one query, but if I'm asking for too much memory, let's say I'm asking for 1 gig and I end up only using 2 meg of that, you still will have that 1 gig for your request for its duration. And you might be gating with other requests that also need 1 gig. And the whole idea here is if you're asking for too much, we don't give it back, and you can therefore slow down overall query concurrency. And then what other cost or risk of misestimation is you might have to refactor your code. So in the example of an MSTVF, or multi-statement table valued function, you might need to rewrite it to an inline table valued function. You might need to put it into a stored procedure. But the whole idea is that sometimes you might have to work around the misestimates that we're making. So in terms of an example, so we have an actual SQL statement here, and I'm selecting from a fact table and a dimension table, and I'm also joining to a multi-statement table valued function, or MSTVF for short. And developers tend to like MSTVFs or functions in general because I can reuse them, I can encapsulate code in one spot. However, from a DBA perspective, you might find that it's not a good thing because there's a fixed estimate that we use for MSTVFs. And I'll show you an example plan right here. So this is a subset of the plan, and you see here that there's a table scan for an MSTVF, and we're estimating 100 rows. So you see in yellow, estimated rows of 100 versus 500,000 rows for actual rows flowing through the plan. And because we're making this 100 row estimate, you'll see downstream we're making decisions that likely aren't going to be good for overall performance. So we have a nested loop operation, and that's just 100 row assumption, but we have 500,000 rows flowing through that. And we also have things like memory grant spills. So we're asking for a memory grant with the assumption that we have 100 rows that we need through that plan, but with 500,000, we need much more memory. So now we're spilling to disk, and then performance suffers. So with SQL Server vNext, we're introducing a new feature family called adaptive query processing. And the first feature I'll talk about is interleaved execution. So I've already mentioned MSTVFs. And what we're going to do is for the first time, we're breaking the pipeline between query optimization and execution, and we're allowing an iterative approach. So if we see a query that has an MSTVF in it, we will optimize up to the point of that MSTVF, we'll execute it, we'll grab the cardinality estimate, we'll revise the downstream optimization process to then use that new estimate. And the idea here is that we'll get a better quality plan based on that informed decision. Second area is batch mode memory grant feedback. And the concept here is that I might have a query that spills to disk, or I might have a query that is taking too much memory and I'm only using a small portion of it. And if we find that this happens, we will update the cache plan memory grant information so that consecutive executions can then benefit from that adjusted memory. And we'll keep adjusting until we get it right and then leave it where it is. And then the third is batch mode adaptive joins. And the concept behind this is I have a build input and I'm making an assumption about a join algorithm that might be optimal. But if I don't exceed a certain threshold, then I'm going to go ahead and use a nested loop operation instead of a hash match operation. So the idea here is if it's a small result set, let's go with nested loop. Large, let's go with hash join. So with that, let me demonstrate all three of the adaptive query processing features. I'm going to start off by setting the Wide World Importers DW database to compatibility level 130 so you can see the prior behavior of MSTVFs and then show you compatibility level 140 with interleaved execution. So this query right here, it's similar to what you just saw. I'm selecting from fact order and joining to stock item. Let's go ahead and execute this, and I'm going to include the actual execution plan. And this is the prior state. So this is what developers and DBAs are used to. It might take, I think, up to 10 seconds to run this. In this case, we had 6 seconds, 144,000 rows. And if we look at the execution plan, a few noteworthy areas. The first is table scan. So if I hover over this table scan, it's actually the table scan for the MSTVF. And you can see here that we have estimated number of rows 100 versus actual number of rows 500,000 or so. Now the second area is we have two different warning symbols. So you see a warning symbol here and here. And if I hover over the warning symbols, you can actually see that we are spilling to disk. So you see a warnings right here, and then operator use tempdb to spill data, and you see spill level 2 with one spilled thread. Now, if I hover over the select, you can also see that we have a memory grant of 4 meg. And again, this is all based on the assumption that 100 rows are flowing through the plan. So even though we end up having 500,000, we don't adapt, we don't correct, you're stuck with that plan. Now let's go ahead and change the compatibility level to 140. So I'm going to clear the cache, set it to 140, and then let's re-execute this query again. And this time, by default, you're going to have interleaved execution working out of the box. There's not an option that you have to set for this. So if we look at the execution plan, this time you see that we have the table scan has been relocated. So you see that it's now on the outer position. And you also see, if you hover over table scan, that we have 500,000 rows estimated versus the actual 500,000 rows estimated. So it's exactly the same because we execute it and then we take that updated estimate, which it really isn't an estimate, it's an actual, and we apply it to the downstream subtree. And then other options, or other observations, you see there's a hash join, another hash join, no warning symbols. And if you hover over the select, you're going to see that we have a memory grant of 60 meg. And so we had an increased memory grant because now we're making the proper assumption around rows flowing through the tree. So for the second demo, I'm going to show batch mode memory grant feedback. And I'm going to go ahead and just clear the cache. And I'm going to create a new stored procedure called fact order by lineage key. And I'm going to go ahead and execute this knowing that for the lineage key that I'm sending for this query that no rows will be returned. So I'm executing this, I get no rows. If you see my plan, it's based on a very low row assumption. And now I'm going to actually execute based on a value that I know will return all rows. So in this case, the lineage key of 9 is every row in that table. So what just happened here, I have a stored procedure and I'm sniffing a parameter, and on the first execution, it's based on 8, and so I'm doing a skinny plan execution, and then I follow it up with a cache plan that I'm going to reuse with a value that returns all the rows. And so if you look at the execution plan, you're going to see a few problems. So you see I have 3 different warnings here. So a hash match warning, sort warning, we have a warning at the select itself. And if I hover over the sort, you can see that we have a warning right here. Operator used tempdb to spill data during execution, spill level 8, and 1 spilled thread. So we didn't ask for enough memory because we were basing it on our original skinny plan with a lineage ID of 8. And if you look at the select operator, you can see that our memory grant is 5 meg. Now with memory grant feedback, we can help consecutive execution. So the first execution suffered because we were using a parameter sensitivity issue plan with a value of 8 as an assumption. But let's go ahead and re-execute this query again. And keep in mind with memory grant feedback, what we'll do is we'll modify the cache plan so that the memory amount gets increased or decreased based on what we need. And if you look at the execution plan now, you see that we have no warnings. We don't have a warning on hash, sort, or select. And if we look at our select now, our cache plan asks for 176 meg. So a big improvement, and the performance then is helped accordingly. Now for the third demo, I'm going to clear the cache again, and I'm going to execute a store procedure that actually runs some trace flags behind the scenes. And this is because this is a private build, but once this goes into general availability, SQL Server vNext, you just need to have compatibility level 140. And I'm going to include live query stats so that you can see the rows flow through the different branches. So I have a query, I'm joining fact order to dimension stock item, and I have a quantity equals 360. And if we execute this, we're going to see a new operator. This is the adaptive join operator. And you're going to see three different branches. The first branch is our build phase. So we're taking an input and we're scanning all rows in that input, and it's part of our build phase of a hash operation. And then we have an optional branch for the probe phase and an optional branch for the clustered index seek nested loop phase. Now, if the row threshold is exceeded, I will go ahead with a full hash join operation. So we can see here that this branch actually has rows flowing through it. So 672 of 672. And you see that this branch for the nested loop has 0 of 336. Now let's go ahead and I'm going to make sure I deleted any rows with a quantity of 361. And I'm going to do select top 5, insert 5 rows with that value of 361. And now I'm going to rerun this query, but this time using a value of 361 where we know we'll get 5 rows back. And this time, if we actually hover over adaptive join, you're going to see a few different new attributes. So we have actual join type, nested loops, estimated join type, hash match. We also have this adaptive threshold rows. So 49 rows, if we exceed that threshold, greater than equal, we'll use a hash operation. If we don't exceed it for the build phase, then we go ahead and use a nested loop operation. And if you look at the plan, you see that this time, this branch is not used. We see 0 of 672 rows passed. But this time, our nested loop actually has rows flow through it. So we have the clustered index seek, 5 of 99, which means that we reverted to a nested loop operation because with the low number of rows, it's more optimal for a nested loop. Thank you for watching the demo. I hope you have an opportunity to download SQL Server vNext and then also look at adaptive query processing features. Thanks for watching.